Alright, glad you made it to page 2. And we are now looking at example 1, where we're going to evaluate the line integral by two methods. Either A, directly, or both by directly and using Green's theorem. So I'm not going to spend too much time going over A, just because we already know how to do these directly. But so here we have our integral. And we know that it's on a simple closed curve because of the notation that it gives us. We have the integral with the circle through it. And our function is xy dx plus x squared dy, where C is the rectangle with vertices 0, 0, 3, 0, 3, 1, and 0, 1. So because it already told us, we're on a simple closed curve by the notation that it gives us, we know that we're also going in the positive direction. So we're going from C1 to side C2 to C3, C4. And so we're going in the counterclockwise direction. So C is the rectangle that we have here, and our vertices are at 0, 0, 3, 0, 3, 1, and 0, 1. So what I'm going to have to do is I'm going to have to take, the integral of all of these by each side. So I have C sub 1 defined as x equals t, because that is what's changing. It's a straight line. And my y is going to be 0 because my y is not changing, and I'm going from the integral between 0 to 3 for t. C sub 2, x equals to 3, y equals t, because that's what's going to be changing. And again, you don't have to necessarily have all of these the exact same way that I do. But once you've found your C sub 1, C sub 2, C sub 3, C sub 4, now our integral of xy dx plus x squared dy, we can break this up into 4 separate integrals. And all, I did here was substitute in, what each value was. So it was like x, so I take my x for C sub 1. So, I should probably put this above here. So let me just do this real quick. So this would be C sub 1, C sub 2, C sub 3, and C sub 4 for each line integral that we have. Make that 4 a little bit better. And so when we're substituting in, when I substitute in this x for x, so that's t, and then y is 0, that cancels the whole thing out. So that whole first part 0. And then this x squared, so I have t squared, but then dy is 0 dt, so that's all 0. So that's why it's just 0 dt. And I did the same thing. I'm just substituting in each value that I have. So C sub 2, I'm going to substitute in, into my equation. And in this case, I'll just get 9. When I substitute in for C sub 3, I'm going to get 3 minus t times 1 times negative dt. And then I'm substituting for C sub 4. I'm going to get 0. So, substituting in all those, I end up with the integral that I have, and then I'm just going to integrate the ones that I can. And so I can't integrate that, so that just goes away. I can integrate this one, which is just 9. I can integrate this one, which is just 9t. And I can integrate the third one, C sub 3, and that's going to give me negative 3t plus 1/2 t squared. And then, again, I can't evaluate that last integral. So I do both of those. And after integrating, I get 9/2. Now, because I'm on this simple closed curve, and I'm trying to find the line integral, I can just use Green's theorem. And so Green's theorem is you're going to take the partial of q, so there's q with respect to with respect to x, which we have there. And so here, I'll just put everything down here. And we take minus the partial of p with respect to y. So that's what we were going to have there. And again, we're doing this over the double integral. And so here's our double integral. For x, we go from 0 to 3. For y, we go to 0 to 1. And so I have dy dx. And I'd go ahead and do the partial derivative. The partial derivative of x squared with respect to x is 2x. Partial derivative of y of xy is just going to be x. And so we have 2x minus x, which is just going to give us x. because I have x and no y's, I can break up the integration because it's a double integral. So the integral of x is just x squared, or 1/2 x squared. The derivative of 1 dy is just y. Substitute in. I'm going to have 9/2 minus 0 for x, and then 1 minus 0 for y, and of course that gives me 9/2. So here you can see through both methods, either going directly or going using Green's theorem, we get the same value. But again, without having to find all of this, I can find the line integral just using Green's theorem. So again, Green's theorem is very useful. Let's go ahead and do the next page too, because I don't think that took too long. No, we'll stop.